side.
So questions from the audience? Yeah.
Earthquake, how is it going to, what are they designed to help it survive an earthquake?
Yeah, it was interesting that the Bay Bridge can survive 8.5.
Well, they don't give you a number. They always say an earthquake in 10,000 years.
Yeah.
They don't quote the numbers. So. Whatever
Yeah,
that
if I-
means.
Well, I read that, and we're overdue supposedly for a
right.
9 at the coast. Probably be upwards of. So what can this?
David
What kind
knows
of
some-
punch can this bridge take?
If I lived in Portland, I would be just as happy on this bridge as anywhere else in Portland.
Or even under
Yeah,
it.
me too. Right.
Even under it, it would be okay.
Yeah, I mean, it's designed, earthquake, well, it governs a number of things, but
there anything
in
we
this part of the country, earthquake dominates the design of the foundations. The tower actually, you know, the bridge deck is very stiff. The demands on the upper tower and the bridge deck itself are not that great, but the demands on the foundation are pretty substantial, and it was designed very thoroughly for probably a bigger earthquake than you're ever going to see around here. So,
Also,
in fact, I would certainly be on this one and not on the I-5 bridge.
David, you might, David, you might talk about the expansion joints, the 18-inch joints in the bridge that help in an earthquake. You know?
Yeah, if you get into a large earthquake, you usually sacrifice the expansion joints. In a moderate earthquake, you know, it's designed for operation. But if you get the big one here, you would end up the expansion joints obviously allow movement, and
Right.
they would clap with the maximum displacements, and you'd have to replace them. But you'd happily do that because the rest of the bridge would be fine.
See, like on the bridge we're doing on the Bay Bridge in the eastern span, we have a 3-foot gap to take, you know, the expansion contraction you get from an earthquake. And here it's about, I guess, 18 inches
Yeah.
or something. So
It's
but
not-
it's a
not
different
bad.
kind of structure. It doesn't move the same way.
Much smaller design earthquake, though.
Yeah, right.
So one of the things about the earthquake that we could experience, the really bad one, is the duration, which is very different than the Bay Area. They're pretty quick.
they
Whereas
can
here
be
we
long
could
too,
see
though,
7
yeah.
or 8 minutes of shaking.
Not 7 or 8
Not
minutes,
7
but
or
a
8.
couple minutes. But
Two
the subduction zone event is far enough off. The subduction zone event that you're talking about, that's the long shaking with a high energy. There's high total energy, but that's not the worst earthquake on this bridge. There's a higher magnitude or higher ground acceleration earthquake that's higher than the subduction zone, and the same is true for Selwood, just up the river. The subduction
So that's more of a
zone.
local fault, you're saying? as
Well, the
opposed to
subduction zone is out at the Juan de Fuca Plate where it's diving under,
Mm-hmm.
and the other earthquakes are slip faults within the crust here, which is, well, I'll let the geophysicists argue about what's real and what isn't. But historically, the subduction zone events are the ones that there certainly is a lot of geologic history for. Whether the other events, the slip fault events, are real or not is a matter of debate around here. You know, we had, in 2001, we had an earthquake up in Olympia area, which was pretty much reasonably within the recurrence interval up there, and other than we got a nice bridge job out of it because it knocked the bridge apart, but other than that, it was not that severe of a, it was just not that severe an event compared to what you see in California.
No, like what happens where we are, there's earthquakes go back and forth, but they also, the one we had, the Loma Prieta in '89, they had a vector, an element that was upward, and that caused the deck to collapse. And on the old bridge, it's being torn down now. So I think the dynamics of earthquakes in certain cases are rolling. You know, they have different stress. In the old days, in the 20s and 30s, they thought the back and forth motion would be it, but it isn't. So that's something else. And I don't know what it's like here, but David and Semyon can talk about that, but on the bridges I've worked on in California, we're always concerned now about that upward motion as well as the horizontal movement that goes back and forth. So.
Other questions? Yeah.
Anything I know about bridges is from Petrosky, and he writes that engineers, push the limits some percent beyond what people have done before. With respect to the earthquake design and people have learned about, from instrumentation about earthquakes, not the materials of bridges, but about earthquakes. Were you challenged in that from the time that this was going to be designed, that a whole lot more was learned about the way this or any other bridge could fail in an earthquake because of better instrumentation and greater knowledge about what happens to structures in earthquakes? Or it's just like materials are better and people are smarter and just
Well, the detailing is not in the course of the design of this bridge, but in the last, I don't know, what, decade or decade and a half. Losing track of time in my old age, maybe 2 decades.
No, 20
But-
20 years.
But 20 years.
Yeah, 20 years ago.
So the detailing and approach to resistance to earthquakes has changed a lot. The recognition of the ground motions has advanced some. The analytical capabilities have advanced more substantially. So our ability to take ground motion records, and we still use, there are people who try and synthesize ground records based on the local geology. That's not used very much, except in research papers. For the most part, we take ground motion records, a lot of which come from California. We've done some bridge up north where the records actually came from Taiwan because they were just the worst record they could get with a vertical earthquake, was higher than the horizontal. But our ability to take those records and apply them to the bridge now is pretty sophisticated with the computers. And so we can get the demand basis on the elements of the bridge. And what also has progressed in the last, really decade or decade and a half is the testing and the knowledge of how the members or elements are going to behave in an earthquake, which we term ductility in terms of the ductility-based design. So they're demonstrably safer. I mean, these cases that, like the Bay Bridge that flipped off the support, and the Loma Prieta, the viaduct in Oakland there that fell down, none of these bridges are designed like that anymore.
Right.
The articulation and the support conditions just are, all the continuity is there. And in a very extreme, if you got an earthquake that was much larger than you anticipated, you would have to do repairs. You would have concrete spalling off and things, but you still wouldn't lose a bridge.
Okay, question is not about earthquakes.
Ah,
You had your hand up and I missed you. Yeah.
Could you explain the design of the piers at water level and below? They were massive compared to the rest of the upright structure.
Earthquake.
How deep do those footings go?
Oh, they go to 160, I think the one of them is 160, 180 feet,
180.
180.
180, wow. Okay, another question. Yeah.
So did you have to take into consideration the differences in live load between an automobile truck bridge and a multimodal mass transit bridge?
Okay, I'm gonna reframe that a little bit, in case anybody didn't hear it. I was curious at what the challenge, how the challenges differ in terms of rail, ped, bike, bus-only bridge versus an automobile bridge. Is that a fair rephrasing of your question? Okay.
I can start, and then maybe Dave can. TriMet is a very discriminating agency. No, just kidding. They don't allow cars on the bridge, so that's a good thing. So
Yeah, right.
only train, buses, and bikers and hikers. So the highest load on the bridge is actually July 4th, shoulder-to-shoulder people
Right.
across this bridge. That is the highest what we call live load. This is, yeah, technical difficulties. This is the highest live load for this bridge. Train load by itself, the train loads TriMet is using are very heavy type trains, and they're substantially higher than the truck loads also. But the key to making this specifically Cablestayed Bridge work is vibrations that are created by the moving train. As a train gets on a bridge and progresses on it, it pushes the wave in front of it because the deck deflects, so the cables elongate, deck deflects, and the train literally pushing a wave in front of it. This wave we have to analyze very, very carefully for what it is going to do to pedestrians and bikers that are on a sidewalk, because we didn't want people, bikers, to start falling off of the bike.
Because
So
of the
this
fluctuation?
this is very, very extensive, a very involved dynamic analysis, and we did it to a great extent to make sure that bridge is viable, that it actually can be bid, and then David and his crew continued.
Yeah, I don't have much to add. It is, as Semyon mentioned, that's the different. One of the differences with a highway bridge is the train. It actually places a different kind of demand. When you have a highway bridge, you don't have. You've got a random crossing of trucks and cars. Cars don't do anything on a bridge, so it's all trucks. Whereas here you have long trains, and the demands on the tower and the demands on the backspan are quite a bit more substantial with a train. But one of the nice things about the concept that was put together here with this bridge in terms of making it concrete is those vibrations Semyon is talking about are demonstrably less. If you're out in the middle of the bridge and you're stopped, if you're not on a bike or anything, if you're just walking and stopped, you'll feel some motion, and your sensibility is all, you might be moving 5 millimeters and you'll think it's a foot if you're out in the middle of the water. Some people will anyway. But actually this is a very rock solid, stable cross section, and the mass of the concrete helps tremendously, as opposed to if it were a steel bridge, it would move quite a bit more and you'd feel it quite a bit more than you will on this one.
So I want to understand this correctly. So the highest loads, gravity loads on the bridge will be when it's filled with 4th of July.
Fresh load of
yes.
revelers?
people on sidewalks is always the highest load.
Yes.
Huh.
It is the highest load because it will be rail to rail. And TriMet wanted us to design for this load. When we were putting together design criteria, we approached TriMet, talked to Rob, talked to Steve and Dave Tertanian on the subject, and asked them, look, will you allow for big events like July 4th, will you shut down the bridge for rail traffic and allow people
Just beyond.
unlimited crowd?
Now what if they all start
And
jumping?
they said
Depends
yes.
what frequency.
And we told them, okay, that adds a very substantial load to the bridge, so be sure. And they told us to look into it and give them feedback. What does it physically means? Would it indicate any changes to the bridge? And again, we had to look at the vibrations, at what we call pedestrian comfort. So if people some of them are running and some of them are walking at a certain distance between the groups of people walking, all those loads have different vibration characteristics and will impact people differently. So we take it very seriously, and this kind of analysis.
I was
for
once on the
pedestrian
Hawthorne
comfort.
Bridge during the first bridge festival, and everybody started jumping. And it was a little unsettling, I had to say. It was like,
I'm giving an example of what he's talking about. And the Golden Gate Bridge is
it's
loaded
8
with
feet.
people, just about 200,000, and the bridge went down about 8 feet.
Yeah, it's 8
Leveled out, and they started rocking it, and the bridge, the main span got a hinge at either end of it, so it can go back and forth and up and down. And that scared the heck out of everybody, and they got them off there, and they won't allow that to happen again. But it gives you an idea of the weight of people on a bridge. It's way beyond trucks and trains and pedestrians, and that's a good example. In the Bay Bridge, I tried to get them to put a bike path on both sides. They put it on one side of the main span. Because of that loading, the eccentric loading, they had to put ballast on the other side to balance it up. And so we could have had a bike path maybe on both sides if they'd realized that ahead of time. But that's a problem, and the layman has no understanding. When it's packed with people, that's the highest load it'll ever get, and that's the reason I brought that up.
in the back.
What design standards did you use on this, and did you find that it was more convenient at times to look at some of the stuff that had been done in other parts of the world and try to apply it to this structure, or were you able to do it all within like the LRF?
Well, from the architectural point of view, we take each bridge and match it to its region, whatever forms we find in the metaphors, and I'll pass it on to the engineers now. But we try to make each one unique, and sometimes that's not really in the program. They now have visual quality analysis, a lot of design-build projects to bring that in. But cities now are using bridges as signatures and branding, and so it's really important that when you put a bridge up, it's going to be there 100 years, and so it has that spec now that's being put in probably. That's from our point of view, that's important.
Okay, I will answer this question, and then Dave, you jump in and add to it. The primary code for the bridge design was Ashtel RFD. That's the primary code. We also used other codes and publication. I mentioned several times how important are, for us as designers, how important was pedestrian comfort, that we analyze for trains on the bridge. We also analyze for people walking, running, jumping, and all kind of other loads. The best publication for this type of analysis is French publication by French railroad company, etc. That's very widely used and adopted. We use it, and I believe Dave Goodyear and his crew also use the same. We use other publications like PTI publication for stay cable bridges, which pretty much became a code for stay cable bridge design.
Yeah, as far as going beyond the American codes, the LRFD. For those who don't know, the LRFD is the AASHTO National Bridge Code for highway bridges. And it has a full complement of design standards for all the elements of the bridge. The PTI recommendations cover the stay cables, which are not in the AASHTO code. But the idea, while we do work all around the world, we are quite familiar with other codes. It's not a very good idea to mix and match codes, because there are things called reliability indices. They're a function of both demands and capacities and certain factors. Different parts of the world have different vehicle loads, and those vehicle loads are factored into the reliability and the index for the bridge, which is the probability of it failure, which is usually somewhere between 1 in 5,000 and 1 in 10,000. If you start mixing parts of different codes, you just lose your bearings, you lose your frame of reference on that reliability, and it's usually not a good idea.
Now, let me just add.
Okay, over this side of the.
I'm going to add something real.
Oh.
It's not like a building. Buildings have building codes and planning codes, but bridges usually have peer review panels that review all the work. On the Bay Bridge, there's no real codes other than AASHTO that we used. It's from our point of view, and there are certain standards. So it's not like a building, let me put it that way, and I think that's the best way to understand. And the proportions are different, the loading, it's so different than building design, and that's why some architects have a hard time working with engineers, because you can't apply with the way of thinking about buildings with that, in the same form, and so it takes extensive experience to get that understanding.
Yeah. One. Everybody hear that? He was asking about whether the cables at some point will need to be adjusted, and how will that happen, if so?
Okay, I will start again. The stay cables don't need any adjustment due to live load in the bridge. They're sealed. You saw maybe the photos taken under the deck. You could see the tubes sticking out from the deck. That's actually the sealed end of the stay cable. However, stay cables are designed so if needed to, they can be opened up and inspected. And if needed to, they can be replaced. They are multi-strand cables. The largest cable on this bridge is 108 strands. So it can be, they can be kind of jacked up, the stress in it reduced, and then one strand at a time removed. And the bridge is designed to function without one or even two stay cables. So I hope it answers your question, Dave.
Yeah, I think your question may have been, as I understood your question, is the cable going to slip in that saddle? And the answer is no. The weight and the friction, the saddle is designed, and actually the analytics are there to verify that the cable will not slide. Although during construction, when you saw it was an open system, that was one of the constraints on building it, is to make sure that cable did not slide, because it would be a very bad day if you, controlling all the geometry and all of a sudden the cables slid, your geometry would go in the tank. So we had to watch that.
So I wanted to ask you guys, maybe we find this little difference in outlook on between engineers and architects. So the Maillard Bridge, the Swiss bridge that we looked at, the 1929 bridge, the engineer himself said that even it cannot lay claim to complete sincerity of form. And so in the end, he was kind of disappointed in his own bridge, even though now, we hold it up as this extraordinary sort of act of minimal elegance and engineering prowess. And so that sincerity of form, I really latched onto that. And I'd be curious about, sort of on a scale of 1 to 10, where you would rate the Tilikum Crossing in sincerity of form.
Well, you would, you mentioned the difference between engineer and architects. You might get a different answer from an engineer and an architect. In terms of Maillard's bridge, as I mentioned, that was sort of mid-time, a little past mid-time in his career. And when he was referring to sincerity of form, he was looking for the, he followed the adage of form follows function. He was looking for, he did not want to put a grain of sand or a pebble of concrete in a bridge that wasn't necessary. He was looking for minimization. So you see his first bridges actually they almost looked like a box girder. They had a complete wall, and then he saw, it was all empirical for him. And
okay, so Tilikum Crossing.
So Tilikum Crossing, in terms of the engineering efficiency, I think Semyon covered that well. It's kind of in between. So from the functional standpoint, there is an investment in the beauty of the bridge and all of the things that Donald explained. That is an investment. From the engineering standpoint, we would look at more of the looking for a form that was perhaps more efficient. From the architectural standpoint, obviously what you have is worth the investment. But so from the Maillard, who you're quoting, from Maillard's standpoint, I would say no. From the architectural standpoint, I would say yes.
Anything to add, Donald? Simone?
No, I think Dave covered it very well. I believe we promised TriMet to create a beautiful, constructible, and affordable bridge, and that was our motto at the first presentation back in April of 2008, and I believe as three of us as a team and all the people who work with us managed to achieve that. So.
Now, I can give you from the architect's point of view, okay? There's certain amounts of redundancy in a bridge, and this one has minimal of that. And in the Golden Gate, it's full of redundancy. There's fake arches. The arch that goes over Fort Point was a fake arch, so it framed the fort. It's now been activated in the retrofit, but there's all sorts of things in that bridge. The chevrons in the towers, the cross trusses between the legs. And so I use that as a metaphor when I talk to engineers, that this bridge is considered one of the landmarks of this part of the world. And the reason is it goes beyond just engineering. There's another element to design that's there, and it's a sense of proportion. And some proportions, if you give an engineer to design a column in a house, it's a steel post, it'll work at 3 inches, and you look at it and say, my God, that doesn't look, better make it 6 inches square. In other words, there's certain elements in design, and most engineers will say, look at an airplane, how beautiful it is, but it does one thing, it just goes through space and lands. It doesn't have people on it, and inside it, of course. But so the form follows function was a big thing, but now people are realizing there's more than that in a bridge or in a building, and so you see things that are now more redundant, but they enhance the aesthetics of it. And so I talked about the illusion of when you have two parallel lines rising, how they expand at the top, and how you bring it in and tighten it up and make it so it tapers up. And that's more expensive than just going straight up. We're working on a bridge in Kentucky. We had a big argument with the engineers because then the contractors designed, built, and we had a tapered tower, and they made it straight up, and it just doesn't look as good. It looks like it widens at the top. And so anyhow, and you can look at the Parthenon if you want to get into the history of architecture and see how they dealt with proportion and shape, but it's not always the most efficient way. But it also, there's that element, and even T.Y. Lin of the firm that David's with, when the T.Y. Lin was alive himself, he said the architect in many cases enhances the bridge, and even he said that. So it's one of those things that, and the Ruckachucky Bridge is one of the things he said on, but anyhow, that's okay. Yeah.
So with the three of you guys here, I can't help but want to ask a question about our next bridge. Now, this is 6th Street Bridge in L.A.,
Right.
which was a historic bridge. I mean, it's been in all these movies. I mean, you know, absolutely iconic bridge, you know, to the Los Angeles mindset. And we're getting this next. This is likely to be our next bridge. This is the Burnside Bridge, and this has been identified as either needing a really, really serious upgrade for seismic because it's on a main safety corridor, or it needs to be replaced. So, and it's probably going to be a little bit of a historic preservation battle here. So one by one, up or down, Burnside Bridge.
You mean to save it or replace it?
Save it or replace it.
I'm in the business of replacing it.
Simone.
Well, I can tell you that as an architect, it represents another period. And any time you have a historical bridge, if you follow the 106 federal guidelines, you're supposed to replace it with a state-of-the-art at the time. And I went through that, and I've been on the Golden Gate Bridge for, I guess, another 20 years. I started in 1980. I've done all the most of retrofitting as an architect, and the engineers, of course. And we always put something new on it, but we take the best we can find at that time that does a thing called solids and voids. The idea is to come back so you haven't messed up the proportions, and so we go through a solids and void analysis. And this bridge would probably fall into that place. And how you treat that and how you present to the public is really important. But it should be replaced because it's over. Today you can do much thinner. It doesn't make such an impact on the environment. Just the footings on that, just looking at it, you know it can be better done. So its idea is it should be replaced. It's not safe, and that's number one.
Okay. Well, I want to thank you guys and briefly flash my next lecture, Michael Singer. I hope you all can come. I want to thank you for tonight.
Yeah,
I want to thank Kiewit for sponsoring, and most of all, I want to thank you for designing a really great new addition to the city. So,
Thank you.
and there's a little party out on the deck that you should all join, and you can ask the questions you didn't get a chance to ask, and it's a beautiful night out, and we can look at the bridge.
Thanks a lot.
You bet.
Good job.